Hi and welcome to this video on entropy and spontaneity. This is the final video in this series about Achievement Standard 91390, otherwise known as particles in thermochemistry. I hope you found this very useful. Right, so just to rip into this is the final part of this topic. And what we're going to look at in this video is, first off, what is entropy? How can we figure out whether the entropy of a reaction is increasing or decreasing? And how do we then relate that back to the spontaneity of a reaction? I'll also have a quick look at how to answer an exam question on this. Okay, so first off, entropy is a measure of randomness or disorder in a chemical system. That's a simple measure. And creating order requires you to put energy in, while creating disorder really just seems to happen spontaneously. I want you to think about your bedroom, your desk, your teacher's desk, your classroom. I don't care what you think about, but any place where people live for a second, I want you to picture how it sort of automatically becomes messy. And you don't seem to need to do anything and it gets messy, but tidying up requires energy. And the same can be said in a chemical system. Messiness just sort of seems to happen. Tidiness requires work. Okay, so when we talk about entropy, really we're thinking about a change in entropy as we go from the reactants to the products. And the things that can affect that are the number of particles. So if we go from a smaller number of particles to a large number of particles, we're automatically going to get more disorder. And the state of the particles. So if you think about it, gases are by their nature more disordered than liquids, which are more disordered than solids. So when we think about the change in entropy, which is sometimes given the chemical symbol delta S, what we're really thinking about is, are the number of particles increasing or decreasing? And are the states more or less disordered? Now, it's not always totally clear cut because you could have more particles but a less ordered state. So there needs to be a bit of logic and thought applied. But in general, if you're being asked to figure this out, particularly in NCEA, the answer will be relatively clear cut, and I'll show you some examples in a minute. So in general, if you've got more particles and the states are more disordered, or the states are more disordered, then you're going to have a positive change in entropy. It is going to be becoming more disordered or more random. If you have fewer particles or the states are more ordered, then the entropy change will be negative, so it will be becoming more ordered. Okay, now that's what's happening within the reaction system. We also need to consider the entropy of the surroundings, because overall a reaction will be spontaneous if the overall entropy change, that system plus surroundings, is positive. So if overall there is more entropy, more disorder, more randomness, then the reaction will be spontaneous. If there is not, so between the system and the surroundings, if everything becomes more ordered somewhere along the way, then actually it will be not spontaneous. So the entropy of the surroundings is determined by whether or not the reaction is endo or exothermic, in simple terms. So if a reaction is exothermic, then heat is being released into the surroundings. That means the surrounding particles are getting hotter, they are gaining energy. As we know, when particles get hotter and they gain energy, they move faster, therefore becoming more disordered purely by their nature. So an exothermic reaction is going to lead to an increase in the entropy of the surroundings. If you have an endothermic reaction, then the surroundings get colder. Colder particles move slower. Things that move slower have less randomness and less disorder. So in other words, an endothermic reaction is going to lead to a decrease in the entropy of the surroundings. Okay, so for a reaction to be spontaneous, if the entropy of the system and the surroundings are both increasing, then the overall entropy of the system and the surroundings combined must be increasing, therefore the reaction must be spontaneous. Similarly, if the entropy of both the systems and the surroundings are decreasing, and the overall entropy decreases and the reaction cannot be spontaneous. Where it gets somewhat more interesting is if one is increasing and one is decreasing, in which case it may or may not be spontaneous depending on which one is bigger. How will you know? You'll get asked in your exam question. It will say something like, explain why this reaction is spontaneous even though it's endothermic. Or, even though this reaction is exothermic, it is not spontaneous. Explain why. So they will phrase it in a way that makes sense. So here's an example exam question. This is straight out of the 2019 NCEA exam, and it's about the reaction of ammonia with oxygen. So there's a nice balanced equation there. You'll see they've got states as well, and there's an enthalpy change provided. And the question asks you to justify, in terms of the entropy changes of the system and the surroundings, why it is spontaneous. So you're told it's spontaneous. You don't need to try and figure that out, but you need to be able to justify that position. Now, I have a bit of a template that I would recommend you use for an answer. You do need to think about it a little bit, but here's how I would structure it. The first, it looks very big, but that's because it's a PowerPoint slide. So start off by talking about the entropy of the system. Is the entropy of the system increasing or decreasing? Are there more or less particles in the products compared to the reactants? Is the state the same, or is it becoming more disordered or less disordered? So that's the first thing. You need to talk about the entropy of the system. Usually there's an achieved point for, actually sometimes even a merit point for discussing the entropy of the system properly. Then we talk about the entropy of the surroundings. So are they increasing or decreasing? Is the reaction endo or exothermic? Are the surroundings heating up or cooling down? Are the particles gaining or losing energy? Therefore, is the entropy of the surroundings increasing or decreasing? So again, usually a merit point for discussing that. And then an overall statement. Overall, the reaction is spontaneous because, and then either they're both increasing or they're both decreasing, or one is increasing and one is decreasing. And therefore, there must be an overall increase or decrease in entropy, yada, yada, yada. Okay, so what does that look like if we go back to our exam question? Well, here's how I would answer it. And this is particularly how the markers wanted you to answer it in 2019. So we've got the balanced equation there. If you look at the balanced equation, you can see in the reactants, there are 4 moles of gaseous ammonia and 5 moles of gaseous oxygen. So there are 9 moles of gaseous reactants. In the products, there are 4 moles of gaseous nitrous oxide, or nitrogen oxide, and there are 6 moles of gaseous water. Therefore, there are 10 moles of gaseous product. So we've gone from 9 moles of gaseous reactant to 10 moles of gaseous product. So let's say that in this reaction, the entropy of the system is increasing because you go from 9 moles of gas particles in the reactants to 10 moles of gas particles in the products. That's it. Now we can look at the surroundings. So if you look at the enthalpy change, right, it is negative 906 kilojoules per mole. Because it's a negative number, it must be exothermic. So state that the reaction is exothermic, which means that heat energy is being lost to the surroundings. Therefore, the particles in the surroundings are gaining heat energy, which makes them move faster, increasing the entropy of the surroundings. Now, a final statement linking the overall entropy change to the spontaneity. Because both the entropy of the system and the entropy of the surroundings are increasing, there is an overall increase in entropy, so this reaction must be spontaneous. Okay, now some people, there is another way to consider entropy. Now this way, if you write your answer the way I've given you here, you will get excellence in your NCEA exam for this answer. And making sure, obviously, you've got the details correct. There is another way to consider it. It's what you'll come across at university, and it is generally a more mathematical approach. Now, you can't work on the math exactly because you don't have the math, but the concept is called Gibbs free energy. And Gibbs free energy is based on both enthalpy and entropy. Okay, so Gibbs free energy, delta G, or the change in Gibbs free energy, is equal to the change in entropy minus the temperature, that's in Kelvin, so it's always a positive number, times the change in entropy. Okay, so basically, if delta G is a negative number, if the Gibbs free energy change is negative, then the reaction will be spontaneous. If it's positive, it will not be spontaneous. So the way to think about this, if delta H is a negative number and delta T is a positive number, then the overall answer, so in other words, if it's exothermic, delta H is negative, and entropy of the system is increasing, so delta S is a positive number, then delta G can only be negative, right, mathematically. Similarly, if the reverse is true, so if it's endothermic, delta H is positive, and entropy is decreasing, so delta S is negative, then delta G must be a positive number, purely due to math. So those are the two obvious ones, and then obviously where it gets interesting is if both of them are positive or both of them are negative, then it comes down to the relative size of the two quantities, and you can kind of see that mathematically. Now, if you can't see that mathematically, then please just ignore this slide. Just trying to raise the last 2 minutes out of your memory, go back to the previous one and stick with that. But for some of you, this math will make sense. And if it makes sense, then by all means, keep it in your head. You can answer an exam question like this, as long as you've talked about the entropy change of the system and the entropy change of the surroundings, because that's what the question is asking you for, you can then do your final justification using Gibbs free energy. So you can say, because the entropy change of the system is increasing and the entropy change of the surroundings is increasing, or whatever, then delta G must be negative, therefore the reaction is spontaneous. That's acceptable, but make sure, and come back to this again, make sure that you have answered the question that has been asked. If it asks you to talk about the entropy changes of the system and the surroundings, you must do that. I cannot state this carefully enough. Answer the question that has been asked. Okay? Don't go off half-cocked and just waffle off a whole bunch of garbage. Answer the question that has been asked. And if you can do that, you will be successful. Okay, I hope you have found this series of videos useful. This is Achievement Standard 91390. Demonstrate understanding of structure of particles. I can't remember the name of the whole thing. Anyway, particles and thermochemistry, all done and dusted. Thank you for your time.